Welcome to our channel, and today we're going to help you understand the paper Scalable AI Safety via Doubly-Efficient Debate. The paper by Brown Cohen et al. At Google DeepMind addresses the challenge of ensuring AI safety in the context of pre-trained AI systems that perform complex tasks, potentially beyond direct human judgment capability. Irving and his colleagues earlier proposed a debate method where AI models debate each other to break down the problem of alignment, ensuring that AI's actions align with human values, into manageable subtasks. However, the original debate method assumed the use of deterministic AI systems and required an exponential number of simulation steps, which limited its practicality. In this research, the authors put forward updated debate protocols that allow for the alignment verification of stochastic, non-deterministic AI systems. These new protocols require only a polynomial number of simulation steps for the honest strategy to succeed, making the process more efficient and scalable. This is especially significant in scenarios where direct human oversight is impractical, such as when language models draft complex legal documents that are too lengthy for humans to evaluate thoroughly. The paper acknowledges the advanced capabilities of large language models, LLMs, for tasks like following instructions, using tools, and performing abstract reasoning. It highlights the need for new scalable oversight methods, protocols combining AI-human interactions for training and supervising complex AI systems, due to the impracticality of providing detailed human feedback on increasingly complex AI outputs. The authors aim to create highly efficient methods for training and overseeing AI systems, particularly in high-stakes applications, such as drafting laws or contracts, where correctness as per human judgment is crucial. The text discusses a complexity theory framework for safely training highly powerful AI models to behave as desired with limited supervision. This is important because verifying complex AI outputs can be challenging for humans. The AlphaZero AI, which learned to play Go through self-play, is cited as an example of a model that became superhumanly proficient without direct human instruction. Verification was feasible because it's easy to check who won a game of Go. Key concepts from computational complexity theory are referenced, highlighting that limited verifiers can accurately judge the outputs from more powerful entities. Notable results include that polynomial space computations can be verified in polynomial time, IP=p space, and solutions to problems verifiable in polynomial time can be encoded for verification using only 3 random bits, the PCP theorem. These concepts don't translate when black box human judgments are involved. Central theorems become false in this context. The authors propose a new model, Doubly-Efficient Debate, where 2 AI provers compete to convince a verifier about the correctness of a computation that relies on black box human judgment. They claim to have proven that any polynomial time computation can be verified with a constant number of queries to the black box and linear time interaction with the AI provers. For this model to work in real-world applications, the AIs need to provide natural language reasoning similar to extensive human analysis. This opens opportunities for AI training through self-play and human feedback, as complex computations described in natural language can be verified via human judgment on a single step of computation. The paper's results aim to create training protocols for AI that allow for the correct solutions to be argued efficiently by the models, and for the verifier to check the solutions with a constant and small number of queries to human judgment. This could be particularly beneficial for tasks like writing laws or contracts, where the AI needs to produce verifiable and correct outputs without excessive computational effort or human supervision. In the text, the authors discuss their work on refining AI model training protocols by evaluating only a limited number of sentences from a legal contract, regardless of the length of the contract, which allows for a more scalable method of training the models. They outline the structure of the paper, mentioning that they initially focus on scenarios where human judgments are considered deterministic and follow explicit instructions, Section 5, after which they expand the model to include the variability of human judgment as stochastic, Section 6. Then they address scenarios where models generate solutions on their own and justify them using natural language, Section 7. Related to their work is the debate format by Irving et al., 2018, which involves AI models in natural language debates judged by humans, which can be compared to the complexity class P space and has been extended to NeXT-P with the introduction of cross-examination by Barnes and Cristiano, 2020b. The current text improves upon this by proposing doubly-efficient debate protocols that ensure the honest AI participant can always win with a polynomial time strategy, even against dishonest counterparts with no computational limits. This approach is inspired by earlier work on interactive proofs within computational complexity and aims to allow verifiers to dependably delegate and check computations done by untrusted provers with less verification effort. Further, the text cites work that connects interactive proofs with machine learning, emphasizing the importance of supervising not just outputs of AI systems, but their reasoning processes. The authors also reference various methods for AI safety that involve feedback from humans and other information sources, as well as debates and alternatives to debates for scalable oversight. They then note techniques to prompt language models for complex tasks as motivation for this oversight need. Lastly, the section describes some technical preliminaries that will be used in the paper, including notation for vectors and subsets, and indicates modeling of computations as Turing machines. The text describes a type of computation model known as an Oracle Turing machine, OTM. This machine operates analogously to a standard Turing machine, but has the additional capacity to consult an Oracle function O for answers to specific queries. The Oracle provides answers to queries as a function mapping strings of length L to 0, 1. Oracle Turing machines can be deterministic or probabilistic. When deterministic, they decide a language L if there is a clear yes or no, in terms of membership in L, for the inputs given to the Oracle. When probabilistic, they provide a probability greater than 2/3 for positive cases and less than 1/3 for negative cases. In the context of language learning models, LLMs, M represents the set of rules and instructions in a natural language, while O stands for human judgment or any other external feedback system. The aim is to solve problems that can be described in natural languages and that depend on the Oracle's feedback, viewed as a black box. Problems where the answer is yes belong to the language L, while no answers do not belong to L. The text also includes definitions of complexity classes for languages with respect to Oracle machines. A language is in class NPO if a polynomial time Oracle machine can verify the existence of a witness validating membership in the language. Similarly, a language is in class MAO if a probabilistic Oracle machine with a polynomial function can verify membership with a probability criterion, greater than 2/3 for membership and less than 1/3 for non-membership. The concept of a debate involving Oracle Turing machines is then introduced. A debate features two provers, A and B, and a verifier, V, that communicate via rounds of messages based on input X and the Oracle O. After a predetermined number of rounds, the verifier decides on the outcome based on the messages exchanged. Overall, the text combines theoretical computer science concepts, the role of oracles in computation, and their application to natural language understanding systems, specifically addressing verification of answers by consulting an oracle or external feedback mechanism. The text introduces a concept of a doubly efficient debate in computational theory, which refers to a debate with specific time constraints for the participants and the verifier. In definition 4.1, a debate protocol is defined by three Oracle Turing machines, A, B, V, where A and B operate within a time limit called p-time, while the verifier V operates within v-time and makes a limited number of queries Q. The protocol decides a language L, with a certain level of completeness C and soundness S. Completeness means that if X belongs to L, A can convince V of that fact with a probability of at least C. Soundness means that if X does not belong to L, even a cheating B cannot convince the verifier V with a probability higher than S. The text mentions that for deterministic Oracle machines, the honest prover always wins, C = 1, S = 0, whereas stochastic machines require a gap between C and S, which can be enhanced by repeating the protocol and looking at the majority outcome. The protocol ensures that an honest prover has a higher chance of winning the debate in time, even against a dishonest prover with unlimited computational resources. Doubly-efficient debate specifically refers to the scenario where both provers run in polynomial time in respect to the input size n, while the verifier runs in linear time relative to the length of each oracle query L and in linear or sublinear time relative to n, while making a sublinear or ideally constant number of oracle queries. Section 4.2 explains how this debate model relates to training and using AI. An oracle O represents human judgment, which is accessible to both provers and the verifier. During training, models A and B learn through self-play using knowledge from human judgment. During inference, the debate protocol is followed but without human input. Model A's output is trusted unless Model B identifies an error. Finally, it states that doubly efficient debate can decide any problem that is solvable in bounded space with nearly linear verifier time and only a constant number of verifier queries to the oracle O. Theorem 5.1 states that any language L that can be decided by an oracle Turing machine M within time Tia n and space Sn can be determined by a debate protocol operating deterministically with time complexity O t log t, space complexity Os log t, and O1 number of queries. The proof for this is found in section B. Theorem 5.1's implication is contrasted to a single prover setup in the context of doubly efficient interactive proofs, as discussed by Reingold et al. The current open question is whether the result by Goldreich et al. For time-space computation by interactive proofs can be improved from OS2 polylog t to OS polylog t. The approach for achieving Theorem 5.1 involves A, suggesting a potential middle configuration of the machine's computation, while B takes on recursive subqueries, ultimately allowing the verifier V to check a single machine transition. The text then introduces cross-examination within debate, which is shown to be more powerful as it requires consistency from multiple copies of the debaters. Debates with cross-examination allow both the verifier and the debaters to query independent copies of the debaters without them communicating, and the verifier can choose which parts of the transcript to read. Theorem 5.3 builds on this by stating a debate protocol with cross-examination can deterministically decide L for any language that an oracle Turing machine can decide in time Tn with oracle queries of length L, doing so with a verifier time of OL log t and using only O1 oracle queries. In section 6, a stochastic debate protocol for any language L decides by a probabilistic oracle machine with access to a stochastic oracle O is discussed. This oracle, representing human judgment or natural responses, introduces variability in which small changes in the oracle's distribution can create significant differences in output probability. The text emphasizes the importance of a Lipschitzness assumption for the machine M to handle such fluctuations, ensuring stability in the probabilistic outputs compared to variations in the oracle. The text discusses a debate protocol involving a stochastic oracle and two parties, A and B, who engage in a series of rounds to determine the validity of A's claim about the performance of a probabilistic oracle machine M. A asserts that the probability Mx outputs 1 is at least 2/3, and B challenges this claim. Here's a summary. The debate operates with an oracle O, an input X, and a K-Lipschitz probabilistic oracle machine M. Party A claims that the probability of Mx being 1 is at least 2/3. B disputes A's claim. The debate consists of T rounds, each with specific steps involving proposed probabilities, queries, and coin-flipping protocols. A outputs a proposed probability, and both parties generate random numbers to determine the next bit of the computation. At any round T, B can abort the protocol if it seems A is deviating from the rules. If B aborts, a verifier V samples the oracle to estimate the probability and checks A's proposed distribution. If the difference is significant enough, V outputs 0, otherwise it outputs 1. If not aborted, V outputs the final bit proposed by A. The protocol promises efficiency in terms of the verifier's time and query complexity, especially when K, a constant related to the machine's performance, is small compared to coordinate T. Furthermore, the text states Theorem 6.2, which guarantees that for any language decidable by such a machine within time T, there exists a debate protocol with specified parameters that decides the language with certain completeness and soundness probabilities. Lastly, an example is provided concerning how a researcher might conduct a meta-analysis on the effect of caffeine on learning in college students, suggesting a structured approach to selecting rigorous and relevant studies. The provided text outlines a debate protocol used as part of a statistical or algorithmic process in order to evaluate and possibly include studies in a meta analysis. Here is a summary in English. 1. The process involves performing a statistical analysis using a random effects model. 2. The heterogeneity among included studies is measured via meta-regression. 3. During the process, a machine, referred to as M, uses natural language instructions based on a theorem to guide the debate protocol. 4. The human judgment oracle, referred to as O, is queried to assess the presence of clear flaws in studies, which requires judgment to determine byte 5. In the debate protocol, Model A follows the plan and lists all relevant information to justify its actions, like including or excluding studies and the reasons why. 6. Meanwhile, Model B monitors Model A's actions and can abort the process if it determines that an incorrect step has been taken. 7. If an abort occurs, a specific query about a study is sent to human raters. The outcome of the debate depends on how closely the raters' opinions match Model A's probability assessment of a flaw being present. The text also mentions the use of Lean 4 formalization to define the debate protocol formally and the modifications made in their algorithm from a preceding figure. 9. The debate protocol is formalized using two monads, which handle stochastic algorithms and probability distributions, ensuring that the process works without integration issues. 10. An extended scenario discusses a debate with a witness, where debaters provide a polynomial-sized witness for a complex problem and argue for the solution's correctness. Here, an LLM, likely a large language model, proposes the complex solution, 11. The result ensures that a human judge can verify an argument by examining only a constant number of steps, with the machine M verifying the argument and both the input X and the witness W being provided, 12. The detailed protocol for debates involving a witness is presented, involving deterministic and stochastic oracles, and verifies membership of an input X in a particular language L. The summary mentions various technical aspects, such as the use of probabilistic models, the role of human judgment oracles, formalization through Lean 4, and discusses a special case of debates where a witness argument is used to verify solutions to complex problems. This text is likely from a scientific or academic paper discussing advanced concepts in statistical analysis, machine learning, and formal verification.